Welcome to Global Virtual School. Students, this is your first year chemistry class. I am Dr. Jal Bano, and the topic for today's discussion is molecular orbital theory from chapter 3. Chapter 3 is the theories of covalent bonding. Students, some of the behavior will be explained with the help of molecular orbital theory, and in this topic we will discuss few applications of molecular orbital theory, and this will be continued in our next lecture. After completing this topic completely, molecular orbital theory, you will be able to understand the paramagnetic behavior of the molecules. Basically, paramagnetic behavior is that some molecules shows deflections under the influence of magnetic field, and you will be able to understand the bond order of the molecule. These two characteristics of the molecules, like paramagnetic behavior and the bond order. Bond order means how many bonds are formed between two atoms. They are not explained with the help of other theories. So molecular orbital theory will explain the bond order and paramagnetic behavior. Is postulates, these are very important to understand postulates. Then we will apply these postulates to different molecules, diatomic molecules. First of all, atomic orbital in valence shell of combining atoms, they overlap in pairs to form molecular orbitals. So atomic orbitals, they overlap to form the molecular orbitals, and they pair means one from each atom. Diatomic, so one partial field from one atom and other partial field atomic orbitals from the other atom, and they form the molecular orbitals. And the overlapping orbitals lose their identity, they lose their energy, they change their energy after overlapping. In overlapping orbitals, they must have same size and energy. So in previous theories, there was no concept of overlapping of same size and energy. Different atomic orbitals of different energy, like in hybridization, they overlap to form hybrid orbitals. But in this case, this is the must condition, that overlapping orbitals must be of same size and same shape. Like 1s can overlap, 2s can overlap, but 1s and 2s cannot overlap. Similarly, s and p cannot overlap, only px and px will overlap. And the number of molecular orbitals formed will be equal to the number of atomic orbitals. So the total number of atomic orbitals, like if they are 2, then there will be 2 molecular orbitals. If they are 6, then 6 molecular orbitals will be formed. And out of them, molecular orbitals, half will be of low energy molecular orbitals, they are called bonding molecular orbitals, and half of them will be at the higher energy than the parent atom, that will be called anti-bonding molecular orbital. So like in start, if you have 2 atomic orbitals, they will form 2 molecular orbitals. Out of them, half mean half of 2 is 1, so 1 will be of the lower energy from the parent atom and 1 will be of the higher energy from the parent atom. So they lose their identity, and half will be of lower energy, but the number of molecular orbitals will be the same as that of the atomic orbitals that overlap. And in that way, there will be head-to-head overlap between s and s, or p and p. So that will be called of low energy will be called bonding molecular orbital sigma orbitals, and of the higher energy they will be called sigma star anti-bonding molecular orbital. BMO stands for bonding molecular orbital, ABMO stands for anti-bonding molecular orbital. And the parallel overlap will be between p and p, and of lower, like bonding molecular orbital, they will be called pi bonding molecular orbitals, and of higher energy they will be called pi star bonding anti-bonding molecular orbitals. And the filling of electron will be like that. In the electronic configuration, they will follow the Aufbau, Pauli exclusion, and Hund's rule. And Aufbau is principle, just I'm repeating, the electrons are placed in energy sublevels in the order of increasing energy values of sublevels. So first will be filled, that will be of have low energy, then of higher, and then so on. And the Pauli exclusion principle is that according to it, no 2 electrons in the same orbital can have same set of 4 quantum numbers. And the Hund's rule is that if degenerate orbitals are available for electron, then electron would like to live in separate orbital, and rather they have parallel spin. One is empty and one have the paired spin. So they will live in the separate orbitals with same spin. And the bond between two atomic orbitals is only possible when number of electrons in bonding molecular orbital are greater than the number of electrons in anti-bonding orbital. This will be little explained with the help when we will apply these postulates to explain the bonding between diatomic molecules. If electron in bonding molecular orbital will be higher than anti-bonding, then a bond will be formed. Otherwise, bond will not be formed. So what is a bond order? Bond order basically is the how many bonds are between two atoms, like H2. It has one, so its bond order is 1. And how to calculate the bond order? This is the number of electrons in bonding molecular orbital minus number of electrons in the anti-bonding molecular orbital and divided by 2. This gives you the bond order. Like oxygen O2, it has 2 bond orders, so it means O and O, they have 2 bonds between them. And the relative energies of molecular orbitals are of 2 types. So atoms that have atomic number 8 and above, so these atoms or their ions, like negative ion or positive ion, this start from oxygen has atomic number 8, fluorine 9, chlorine 17. So there is a group that has atoms atomic number greater than 8 and greater than 8. They have a different energy order, and while the other atoms that have atomic number 7 are less, and their ions either positive or negative, they have a different energy order. But this will be explained in detail in our next lecture. Now come to the applications of now we will apply this molecular orbital theory to some of the molecules like hydrogen and helium. I will just compare these two. This will explain the bond order of the between two atoms. Hydrogen atomic number is 1, so 1s1. For other hydrogen it's also 1s1. First of all, this is the energy axis. So energy is increasing in the above order. 1s from the 1 orbital, this is like 1 atomic orbitals. They are of the same size and same shape and same energy. This is 1s, this is 1s. They have 1 electron in each. This from one hydrogen, this is from other hydrogen. Atomic orbitals overlap to form molecular orbitals, their number is same. So those 2 atomic orbitals, they combine to form 2 molecular orbitals. Out of them, half of 2 is 1 will be of at lower energy than parent atom, this one level, and this is this one, and half of them will be at higher energy level than the parent atoms, and these lower one are called bonding molecular orbitals and higher energy are called anti-bonding molecular orbitals. This is between s and n, so this is the sigma bonding molecular orbital, this is the sigma star anti-bonding molecular orbital. And the next is how to fill the electron. First electron will be go to the orbitals that are at lower energy. So at lower energy are sigma bonding molecular orbital, 1 electron according to Hund's rule. This is need to fill the electron, so this will come here and it will pair. If no electrons, still you have electron, they will go to the bonding molecular or anti-bonding molecular orbital. So this is called sigma 1s and this is called sigma star 1s anti-bonding molecular orbital. Now how to calculate the bond order? How many bonds will be formed between number of electrons in the bonding molecular orbital minus number of electrons in the anti-bonding. There is 0. There is no bond. Electrons divided by 2, and this comes 2 by 2, answer you have 1. It means hydrogen has 1 bond between them, and its energy order will be, energy order you can calculate from here. First of all, write from here, because this is of the lower at lower energy, sigma 1s of lower energy, and then this is sigma star 1s. So this is the energy order, and this is called bonding molecular orbital energy level diagram. So when you are asked to draw the bonding molecular orbital energy level diagram, you have to draw this molecular orbital diagram, bond energy, its energy order, and this is a very stable bond, 436 kilojoule per mole energy. of this bond is. Now come to the helium. Is helium exist in diatomic form? You know helium's atomic number is 2. It's 1s2. So helium has like this energy 1s2, and this is also 1s. They have electrons in it. So they will form molecular orbitals. Half of them will be at lower energy and half of them will be at the higher energy. This is bonding molecular orbital. This is anti-bonding molecular orbital. This is 1s. So s and s sigma, and this is 1s, and this is the sigma star. So now fill the electron. You have 4. 1 2 3 4. 1 2. So you left with 2. These will go to the anti-bonding. So these are 4. Now the bond order will be number of electrons in the bonding molecular orbitals 2, number of electrons in the anti-bonding molecular orbitals 2 divided by 2, 2 minus 2, 0, 2, answer is 0. It means helium and helium, there is no bond exist between helium, and its energy order will be like sigma 1s less than sigma star 1s. So this is the bonding molecular orbital diagram. These are diamagnetic. There is no partially filled atomic orbitals in the bonding molecular orbital. This will be more explained in the next lecture about paramagnetic behavior. These are smaller atoms with smaller electronic configuration. Now come to the lithium and beryllium. Atomic number of lithium is 3. So its electronic configuration is 1s2, 2s1. So its energy diagram, energy in this order. So 1s2 will be like previously. So one lithium and other lithium, they have same 1s2, 2s1. So I am not writing it again. I will discuss this now. 2s. These are of the same shape, same size and energy. They have one electron in each. They will overlap to form molecular orbitals. Half of will be at lower energy and half of them will be at the higher energy. Lower energy are called bonding molecular orbitals. They are called anti-bonding molecular orbital. S and S. So this is the sigma and this is the sigma 2s, and this is sigma 2s, sigma star 2s. 1 and 1, 2, 2, and there is no electron in the anti-bonding molecular orbital. So bond order will be 1 and 2. 2 electron minus in antibonding there is 0 divided by 2, so you have answer 1. It means lithium and lithium, they have 1. This is although this is lower, but there exists some lithium diatomic and they have some sort of energy that is about 110 kilojoule per mole. And its energy order will be like from this, previously this will be sigma 1s less than sigma star 1s, and now right in between them, start from lower, that is less than sigma 2s less than sigma star 2s. So this is the molecular orbital energy level diagram. Now come to the beryllium. Beryllium atomic number is 4. 1s2 and 2s2. Other beryllium will be also 1s2, 2s2. So this one is energy. This is 2s and is also 2s. And they have 2 electrons in each. They will overlap to form molecular orbitals. Half of them will be at lower energy, half of them will be at higher energy. This is anti-bonding molecular orbital because this is SS, so this is sigma bonding molecular orbital, and this is 2s, and this will be sigma star 2s. Now fill the electron according to Pauli-Exclusion, Hund's rule and Aufbau principle. You have 1, 2, 3, 4. 1, 2, so 2 left, they will go to the up. So this is bond in order will be like number of electrons in bonding molecular orbital minus number of electrons in the anti-bonding divided by 2. So 2 minus 2, it's 0 by 2, answer is 0. So there is no bond that exists between beryllium. So and its energy order will be like for this same like this 1s sigma 1s less than sigma star 1s. This is less than sigma 2s less than sigma star 2s. So this is the energy and molecular orbital molecular orbital energy level diagram. So when you are asked to draw the molecular orbital diagram, you have to draw the molecular orbital diagram with bond order and energy order. So this was all about the postulates of molecular orbital and a few applications of the molecular orbital. In our next topic, that will be the continuity of the molecular orbital theory, we will apply these postulates to more complicated molecules, diatomic, and we will discuss their energy orders, the difference of the energy orders, and the paramagnetic and diamagnetic behavior of the some of the diatomic molecules.